Hello everyone and welcome back again to the linear algebra component of the Calculus and Linear Algebra series. In the last video we introduced this idea of linear combinations of vectors, and what I want to do now in this video is introduce you to the idea of how to calculate the magnitude or length of vectors, and as well how to calculate the angle between two vectors and generalize that to vectors in Rm. So let's go to the tablet, and we want to start here by constructing a notion of something that allows us to calculate the length of vectors. And this is otherwise known as the norm of a vector. So we start with our definition. And if we say let V is simply just going to be a vector in Rn, so we describe it by these n many coordinates, V1 through Vn. Then the norm, strictly speaking, it's something called the Euclidean norm, but we're not going to address any other types of norms in this course. So the norm of V is defined as the following. We write it as this kind of almost like double modulus sign notation is equal to the square root of the sum from I equals 1 up to n of Vi squared. And you might wonder where this comes from. You might think, well, this is kind of a strange definition, and why does this relate to distance? Well, if you think about, if I put in the case when n equals 3, or let's look even easier at when n equals 2, when I put n equals 2 in here, if I think about what this is saying, so if I draw a picture, and let's say I look at n equals 2, so we have R2. If I draw my picture of R2 and I think about my vector here can be V, this thing can be written as V1 and V2. So if we see here the norm of V, which we'll write in a different color, the norm of V using that notation there above is simply the square root of V1 squared plus V2 squared, which is just simply Pythagoras' theorem. That just tells us that the length of this vector, or the length of this arrow here, is simply just the norm of V. So all we've done now is just generalize that to when we're considering vectors that have n many components as simply two components. And we can also do it for R3. You can equally see that it's just Pythagoras' theorem for R3 again, but it's a bit difficult to draw on the page because we've only got a 2D surface to try and draw 3D things. But you can see that this is just simply an extension of the usual Pythagorean distance to n many dimensions. Okay, so much like everything in Euclidean geometry, where you start introducing a notion of distance, we can also introduce now a notion of angle. And along that line, we want to talk about something called the scalar product. So that we can first talk about the scalar product in this kind of algebraic way, and then it turns out that the scalar product in n equals 2 and n equals 3 has a connection to the angle between two vectors. So then we can generalize a notion of what we mean to say the angle between two vectors, where the vectors now are not necessarily these arrows in 2 or 3 dimensional space, but something in some n-dimensional space. So let's start with our definition. We now have two vectors, so let U equal some vector in Rn, defined as follows, and V equal V1, V2 up to Vm. Then we define the scalar product, so we call it the scalar product. Sometimes you might have seen this as the dot product. So the scalar product of U and V is defined as following. We can write it as U dot V is equal to the sum from I equals 1 to n of Ui times Vi. So note here that this is the product that we define on the real numbers. That's the usual product of multiplying two real numbers, and this here is some new product, some new notion of a product between two vectors, which we call the scalar product. Now, why is that useful? That's particularly useful because something just crashed. Okay, I think that should be back up now. Apologies for that. Okay, so we have now that our scalar product is given by this thing. And what we realize is that, as I said, in the case when n equals 2 and n equals 3, we can write the cosine of the angle between two vectors in n equals 2 and n equals 3 in terms of this scalar product and the lengths of those vectors. And that's simply basically the cosine rule. So the cosine rule, so for when, let's just look at when n equals 2, the angle between two vectors, we would have that u dot v, so the angle between these two vectors u and v, satisfies the property that the dot product between those, or the scalar product, is equal to the norm of u times the norm of v times by the cosine of the angle between them. And that just follows immediately from the cosine rule that you know from GCSE. Now, similarly, you can also do this for when n equals 3, which would also give the exact same result. So what we say then is let's generalize it to a definition that extends to when we're working over n-dimensional vectors, when we're working over Rn. So we then have another definition that we can think of the scalar product. So let's write this down, maybe down here. So we have our definition. So again, let u equal u1, u2 to un, and v equal v1, v2 up to vn. Then we can equally define the scalar product of u and v is defined as, we can write it as u dot v is now equal to the norm of u times the norm of v times by whatever this notion is of the cosine of the angle between them. So we're kind of generalizing an idea of what it means to say the angle between two vectors in Rn, which we can do that now because we kind of generalize this notion of the dot product. So we can see that. Let's just look at an example in R3. This would work for any n, or at least for any n that is natural. So I could do it with R4, R5, R6, whatever it might be, and now can describe a notion of angles between those two vectors by simply defining the dot product or the scalar product. In this situation, right, I can just have the scalar product, and I know how to take the norm of those things, and therefore I can find the angle between them, cosine of theta. So in this situation, we have let u equal 2, 1, minus 2, and v equal 1, 1, 1. Then what is the scalar product between them? So then the scalar product of u and v is what? Is given by, we have u dot v. So we take the first element of u and we multiply it by the first element of v. So that's 2 times 1. We have the second element of u and we times it by the second element of v, which is 1 times 1, and we add those. So we've got 1 times 1. And then we have the third element of u, which is minus 2, times by the third element of v, and we add that on, which is plus, we can write that as, say, minus 2 times 1. So adding those up, we've got 2 minus 2, which is 0, plus 1, so the overall thing is 1. So that's what we get for our scalar product of u and v. The next thing we need to find in order to find the angle between them is we want to find the norm of those two vectors. So the norm of u is given by, we just plug it into our definition. We have the norm of u is equal to the square root of the first term of u squared, which is 2 squared, so that's 4, plus the second term squared, which is 1 squared, plus the third term squared, which again is 4. In other words, we've got the square root of 4 plus 1, which is the square root of 9, which is 3. And we can also find the norm of v is given by the square root of, in this case, 1 plus 1 plus 1, which is root 3. So, rearranging our equation above, we have that cosine of theta is equal to the scalar product of u and v, which is 1, divided by the norm of u times the norm of v. So in other words, it's equal to 1 over 3 root 3. And plugging that in, you can plug that into a kind of calculator, or you could use Python to find that theta is approximately something around 1.377 radians. That's to 3 decimal places. So what we've seen here is that we've constructed a notion of norm, which allowed us to define the length of vectors. We then talked about the scalar product between two vectors, which allowed us to define a notion of angles between two vectors. And this is generalized all the way up to Rn now for vectors in Rn. So these things had some geometric meaning when n equals 2 and n equals 3. We could really visualize it as lengths and as lengths of those vectors, of those arrows, using the kind of Pythagorean theorem. Or we could also just realize the angle between those vectors by using the cosine rule, and using those properties of what we had for when it was n equals 2 and n equals 3. We generalized our definitions so it now worked for dimensions greater than n equals 3. So that's where we're going to conclude the video. And next week, what we're going to start discussing is we're going to start discussing things like matrices and kind of other properties of vectors and other things in linear algebra. So as always, I recommend you read the notes after watching this video and to attempt any problems in the module handbook pertaining to the material discussed in this. So thanks very much for watching, and see you in the next video.